the level integral over general regions. Okay. So in the previous section, it was long, but we are trying to establish its definition and the calculation as iterated integrals for double integrals over rectangles. All right, so now what happens if we have a general region that is not trivial, right? So that's the main question of this section. What if we need to compute the double integral over a general region D of f of x, y, yeah, where our D is just a closed and bounded region. D is closed and bounded. So basically, the notation is simply different by replacing that rectangle R with this hat D, which is a general region. Okay. So, well, the regions in two-dimensional space on the plane could be rather complicated, but we have two types that we start with. Type 1. So we think about, so there are two coordinates. We think about the range of one of the coordinates. Let's say we have x varying from A to B, but then y is cut between two functions in terms of x, okay, which are called G1 and G2. So basically, this is a generalization of what we have seen in the previous section where here, so if you recall, for rectangle, we have x between A and B and y between C and D, right? So here, this is just a simple generalization where we just replace the constant lower and upper bounds by functions. So if D is a rectangle, angular, then y is simply between two constant functions. Okay? So, for example, so basically we just need to establish, in general, two curves, G1 and G2, that are in terms of x. Okay. So it could be the upper bounding function and lower bounding function like these two. So that's the functions y equal to, so the upper bounding is G2, the lower bounding is G1. And here my x is between A and B. And it could be possibly the region upper bounded by the function G2, lower bounded by function G1, and we have two vertical boundaries in dashed. Okay, so that's D. And of course, here, this is the kind of, if you see these vertical boundaries like these, then that's clear indication that this is using, we can say, the vertical bars to sweep along this region from x equal to A to x equal to B. Right? So just use vertical bars to cover it. Okay. But then, in some situations, the boundaries on the left and right, they may not be vertical lines. They may just be somehow degenerated. So you have a single point, something like this. So it's possible that you have two functions branching out of this left end point, let's say. But then we still have low upper bounds when the x value extends all the way to b. Okay, so the region could be something like this, where still the upper bound is g2, the lower bound is g1. So here it looks a little bit different because the left hand side, this is just a single point instead of a vertical dash line. Right? And now, the right hand side could also be a single point. So it could be something like this. Right? And stops here. Right? So this kind of type 1 region can cover all these regions that you have seen if your upper boundary and lower boundary are just functions in terms of x. The upper bound is again g2, the lower bound is again g1 in terms of x. Okay. So we have seen 3 pictures, but basically we just decide, okay, we are sweeping using vertical bars, right? So basically for those vertical bars, we're just choosing x arbitrarily from A to B, right? And then the lower end and the upper end are just 2 points on these function hoops, right? Okay. So I believe these are things that you have seen when you try to calculate the region, the area of the region that's enclosed by several functions. So that's possibly old. Okay? But then we are trying to just define integrals, calculate integrals on these more general regions. More example. So let's look at the unit circle. Well, I would say unit disk. Okay, so the unit disk is definitely something that can be described using the type 1 region. Okay, so here we know that the boundary is x squared plus y squared equals 1, and we know then the region enclosed by this circle is just the disk, right? But then, okay, we actually know that there's a smallest x value possible in the disk, and there's a largest x value possible in the disk. That's on the diameter along the x-axis. So you know the x value is the smallest that's -1, and the largest is 1, right? That tells you can describe this region firstly by deciding the range in terms of x. So that's between -1 and 1, right? So that's just the A and B values. But then we need to decide G1 and G2. So G1 is the lower bounding curve as a function, and the G2 is the upper bounding function of this circle. Okay, so then you need to solve for the y value because here G1 and G2 they are functions in terms of x. Okay, this representing the y value. So here by solving the y value from the equation right here, so this is a simple radical, right? So you see y has to be the square root of the plus or minus the square root of 1 minus x squared. Okay, so that gives you the bounds g1 and g2. So y is less than or equal to the positive square root and is greater than or equal to the negative square root. Okay. So here, simply this is y equals to positive 1 minus x squared, and this is y equals to negative under the radical. Any questions so far? So so that's one way to describe this disk, a unit disk. All right. So here if a function f is continuous over a type 1 region, cat B, then we can define the double integral over this region by the following calculation. So double integral over the region D of f of x, y, dA is, so now we see that x is between a and b, and y is cut between two functions relying on x, right? So we write the interval in terms of x first, and then we write the interval in terms of y in the inner interval. So that's what we do. So x goes from a to b. So here we keep the x outside. And then y is cut between g1 of x and g2 of x. And then we write dy. And then finally we're integrating f of xy. And here I can eliminate the space by moving dx a little bit left. So this is the way that we will iteratively calculate this double integral. So you can see here, this double integral, the inner integral is relying on g1 and g2. Okay, so two functions in the x. So if you interchange the integral order, then this is something different. Okay? So if you interchange the order, you can clearly see the mathematical meaning is different. Okay, because if you think about it, when you integrate the inner, you are getting rid of the variable x from the multivariable function. Okay, so then x is gone. Then what you have left in the circle part is simply a function in terms of y, right? Because this is the integral here is just a definite integral in terms of x, where you should y as a constant, right? So this is so the circle part is only about y, okay? But then now you integrate on the outside, so you're integrating with respect to y, but now you have function upper and lower bounds. So the final result will be a function in terms of x. Okay. And here, what you get if you do the double integral here, this is going to get you a scalar. Because here, in the inner integral, you'll get rid of x. Excuse me. In the inner integral, you get rid of x, get rid of y, right? But then you plug in g1 and g2, you'll get a function only in terms of x. And then on the outside, you do the double integral in terms of x. So that gives you a scalar. So these two are definitely different. So that's clear difference. So this is different from what we have seen in the previous section, because in the previous section, we are integrating over a rectangle. So a rectangle, we have the Fourier theorem. The Fourier theorem tells you can interchange the order of integral integration whatever way you want on a rectangle. But here, the region is different, so we cannot do the interchange of order in this straightforward way. Right, type 2. So type 1, we describe the region by specifying the range in terms of x first, right? So type 2 is, you can say the mirror type, where we now decide the range in terms of y first, okay? So y is now cut between c and d, but then x is possibly upper and lower bounded by h of x and h of, well, it should be h2 of x and h1. The upper bound is h2. Now you see, this is just of course, when you define x, you need the function to y. So basically, as figures, that's really clear. It's just interchanging the order of description. So we still have the xy plane. And then we have, we specify the range of y, let's say from T to D. Okay. So these are not horizontal lines, right? But then, okay, so the left boundary and the right boundary, they are curves, so they are functions relying on y. So exactly h1, h2. So it could be something like this, and something like this. So this is x equal to h1 of y, x equal to h2 of y. So these are the of course lower bound and upper bound for the variable x. Okay. So that's just a different order of description. Okay? But here still we can see for the figure right here, there will be a clear indication of this kind of type 2 region because there will be horizontal upper and lower boundaries, right? So that's kind of straight horizontal line. So that's actually really clear. But it's also possible that these two kind of boundaries can degenerate to points. So let me quickly draw one that's having a single point. Let's say as the upper boundary, so it just splits into two curves again. So let's say this is the largest possible y value. And then for the smallest possible y value is C. And then the region is defined by we have x equal to h1 of y, x equal to h2 of y as the upper and lower bounds for the x value. So when you think about the bars that are either vertical or horizontal sweeping this region, okay, you can think about these are horizontal bars. Okay. So basically, whatever y value that you specify on the left hand side from C to D, you can draw a horizontal bar. Okay? And you can imagine this is a sweeping from the bottom to the top of the region. Right? All right. So this is a straightforward extension from type 1. So let's do a quick example that we look at the unit disk again. Okay. So in the unit disk, here we just need to decide. Okay, the shape definitely can be better. I can move this a little bit to lower. Okay, so here, instead of solving for y, here we solve for x, right? Because here we know that the smallest possible y value is -1 now. And the largest possible y value is 1, right? But then we need the left-hand side boundary to be described and the right-hand side boundary to be described. Okay, so they are functions in terms of y. Okay, so here for a horizontal bar that's covering a piece of this disk, you want to know, okay, what's the left endpoint x value? What's the right endpoint x value? Okay, so here you're solving for x. So now to solve for x, we know that x must be positive or negative, so yeah. I can make the negative roots this boundary of the left hand side. And then we describe the region as the type 2 region by saying, okay, my y is from -1 to 1, and my x is cut between these two radicals. in terms of y, okay, as functions. That's good. So you can see that the type 2 is exactly parallel to type 1, right? And of course, you can define the double integral on the region D in terms of y first. Okay? So double integral over the region D for type 2 region is now we start with so y now is cut between C and D in type 2. So we do y first, and then we know that x is cut between h1 of y and h2. And finally, we still integrate this function f of x, right? Okay. So you can see, so type 1 has the double integral definition in terms of the integrated integral, and now type 2 has a different double integral expression. So the only difference is, well, there are two differences. Of course, the first one is the bounds, okay? And the second one is that the order of the integral is a little different. Okay, so it was dy dx, where x is free. Okay, so here we have dx dy, where y is free. Alright. Okay, so now let's look at one example for the calculation. So let's look at the double integral over the region D of x plus 2y. Okay, dA. So here we are integrating this simple function x plus 2y, and right here the region D is the region bounded by two functions, y equals to 2x squared and y equals to 1 plus x squared. So here you can see the barrier function is not so complicated, but then we want to describe the region D. Okay, so definitely we have to do some geometric representation of the region. Geometry of D. So of course, firstly we need to sketch these parameters. So we can see that y equals to 2x squared is a parabola that's steeper in a sense, and y equal to 1 plus x squared is not as steep, but it's higher at the when x is 0. Okay? So you have this one going through the origin. This is y equals to 2x squared. But then when x is 0, you have 1 for the other curve, but then the other one is flatter. Okay? So if you look at the shape of this region that's bounded by these two functions, then that's gonna be shaded, okay, right here, cut in between, right, closed and bounded. So here we notice that as long as we know where these two curves intersect, then okay, we can do this as a type 1, right? Because obviously we have a function in terms of x, another function in terms of x. So they are the trivial lower upper bounds for the y value. Okay? So if we are using the vertical bars to cover the region, and then x goes from this x value to this x value, and y is cut between these two functions. So that's a straightforward description. So here we definitely need the intersections. So once again, you see that to get the intersections, it's important to solve for the ordered pairs points. So we have y equal to 2x squared as one of the functions. It must intersect with the other function. So we are looking for xy pairs that satisfy both equations. Okay? So make sure to play this yourself. There are two solutions. So basically, this is not so difficult because you can substitute y. Okay, so you can eliminate y by substituting the second y from into the first, and then you notice that okay, the right hand side must equal. So 2x squared must equal to 1 plus x squared. Then that tells you x squared must be 1. Right? So you have x equals 1 or x equals -1. But now you notice that y must be 2 because in either case, x squared is 1. So what does it tell you? It tells you if you zoom up for the shaded region, there's a flatter upper bound and there's a more curvy lower bound. Okay. And then we know this point is -1, 2. This point is 1, 2. And then we have the upper bound to be 1 plus x squared. The lower bound is 2x squared. Okay. So like we mentioned a little bit earlier, this is somehow easier if we just use the vertical bars, sweeping from the left to the right to cover this region, right? And of course, I would like to quickly mention that okay, you can do the type 2. It's just that will be a little bit messier because so basically, if you are sweeping as horizontal bars, then that's going to be fine here, here. But after it hits the upper bounding parabola and it goes beyond, then it's getting complicated. Okay, so beneath that parabola, you can use just one pair of lower upper bounds, right? Like right here and right here. But then if you go beyond and go a little higher, then you will have two pieces of horizontal bars. So that's making the integral a little bit more complicated to describe. Okay? So intuitively speaking, you can see that sometimes for the same region, there could be harder descriptions and simpler description. So there's always kind of a choice, reasonable choice, that makes the problem a bit harder. Right, so let's get rid of that. And so that's described. So in terms of type 1, it's actually simple. So we know now x is between -1 and 1, so we describe that first. X is cut between -1 and 1, y is cut between, okay, so the lower bound is 2x squared, the upper bound is 1 plus x squared. So it's definitely straightforward to write down the iterated integral and then calculate. Okay, so now we have x between -1 and 1, dx. We have y between 2x squared and 1 plus x squared, dy. So it tells you here you are integrating in terms of y first. Then you will get rid of y, and finally the outer integral is in terms of x. Once you integrate in terms of x, everything is equations. All right, let's calculate. So here we just do it carefully. play with the inner integral, of course. So here we're integrating with y and we're treating x as a constant. So write down the antiderivative here. So x is a constant, that will be multiplied by y, for the antiderivative of this part of a constant, right? And now for 2y, so we have a power function. So y is a power function with the power 1, so we add 1 and divide. So this is the power function as a symbol. So we add 1, that's a 2, and divide by 2, so that's y squared. Okay. So that's the antiderivative in terms of y, right? And of course, if you quickly differentiate, that gives you x plus 2y. Okay? So that's something you can always verify by differentiating in your mind, in your head. And now, in terms of y, so we plug in. So the only thing different from the previous section is that, okay, the bounds are in terms of are functions in terms of x. Okay. So here we plug in y equal to the lower bound 2x squared, the upper bound is 1 plus x squared. Okay. So you need to be careful when you are plugging in these functional expressions. So that's the difference in this section. That's good. Right, so now let's be careful. So this is -1 from -1 to 1. So we plug in and we have x times 1 plus x squared. So y, we just for the upper bound, we substitute y here. So 1 plus x squared whole squared minus. So yeah, let's keep it in a pair of brackets to indicate this is the evaluation at the upper bound and the evaluation at the lower bound. So x times 2x squared plus 2x squared, whole thing squared. Okay. So now we see the function that we're integrating after the evaluation is univariate polynomial, right? So I would like to mention that this will not be really hard to integrate. So we don't really have to repeat the steps of doing that calculation. Make sure to check that the final answer should be a fraction 32/15. So somehow you have, so here there's nothing to say, but you somehow need to multiply things out to utilize the power law for monomial terms. So you do have to multiply things out and do calculations. So that's the only thing that we have to emphasize for the sake. Any questions? Right, so let's look at another one. That's integrating a polynomial function again, but the region is special. So where d is, so we're integrating x squared plus y squared. And d is bounded by y equal to 2x and y equal to x squared. Okay. We have the line and the parabola. And here we only describe the region D by this by saying this bounded. So we have to sketch the figure, okay, for the region D in dxy. So we start with the parabola. So that's it's just the parabola opening upwards. Okay, going through the origin. And then we realize that the y equal to 2x is also a line going through the origin, and the slope is positive. Okay. So now that tells you the region that we're looking at is actually the straight region here. Okay. So just cut between your line and the parabola. Okay, so y equal to x squared is the so in the region D, you can see that parabola is the lower bound and the linear is higher, is the upper bound. So still, you can see that either way, you would have to calculate the endpoints. Okay, so of course, one of them is kind of clear, is the origin, which is 0, 0, and then we need to take care of the other one. But whenever you solve it, you will get the two. So computing intersection. So basically, we have, we need to set the two equations to be satisfied at the same time. Okay. So once again, you can do the substitution rule by substituting y, and then you will get a quadratic equation in terms of x. Okay. There will be two solutions where x is 0 or x is 2. Okay. And y is defined in terms of x squared or just 2x. So either way, you will get y equal to 0 or y equal to 4, respectively. So what does it tell you? It tells you we have a line, we have a parabola. So let's zoom up a little bit. So we know that's the region D. So well, let's we don't really need that letter here because that's clear. So basically we just zoom up that region a little bit. Okay, at the bottom right here. So now the left-hand point is 0, 0. This point is upper right corner, 2, 4. Okay, so the upper bound in terms of x is just y equal to 2x. The lower bound is y equal to x squared. Okay. So if you describe the bounds using the function in terms of x, that's just saying, okay, this is choosing type 1, so we are using vertical bars to describe to cover this region, right? So vertical bars to sweep from the left to the right. Okay, but of course this this region is not really to describe if you use horizontal bars to cover this. Okay? So if you use horizontal bars, then let's say okay, my y value starts from 0 to 4, right? But then you need to somehow solve for the x value. So you need the lower bound x value, which is starting from the line. The upper bound x value is starting from is ending at the parabola. But then they are all in terms of y that you specify. Okay, so you specify y value. So then you need to utilize the function equations to solve for x. Okay, so here x is the square root of 1. And here, of course, when you take the square root, there's a positive and a negative. But then, if you look at what you do, the negative one is the negative root, which is not really the one that we want. And we look at the one that's in the first quadrant. Okay, so this is in the first quadrant. And then we can also solve for x by just dividing both sides by y by 2. So x is y over 2. So this actually gives you two kinds of descriptions. So to put them down, so in red we will do the type 1, which is saying, okay, my x is decided first. Okay, so x is between 0 and 2. Okay, so just looking at the x coordinates, x is between 0 and 2, and now y is cut between the functions in terms of x. So the lower bound, excuse me, the lower bound here is the parabola. The upper bound is the line. So 2x is the upper, x squared is lower, right? And now for type 2, it's the xy pair. Now we decide y first, okay, by looking at the y value, it's starting from 0 to 4. And then here, the left hand point and the right hand point of the bar is actually x is half between y over 2. So the left hand point is this one. The right hand point is square root of 1. Okay. Any questions so far? So we can see this region is similar than the previous one in the sense that we have two reasonable descriptions, okay? Both in terms of type 1 and type 2. Okay, so at this point we can say that okay, this double integral can be described in two ways. But let's write them down. So the double integral over the region D of this sum of squares, it can be described by the type 1 double integral. So this is where x is free from 0 to 2 dx. Y is half between x squared and 2x dy, and then x squared plus 2. Okay. That way integrating. So this is the one from the red description. And if we write down the purple, then okay, y is free from 0 to 4 dy. And then my x is cut between y over 2 and square root of 1. Right? So we're still integrating the same function. But you can see that for the same region D, there are two descriptions, and you result in two different double integrals. Okay? And you can definitely verify that if you just either way, you will be able to calculate and get down to the final answer. So they eventually will be the same. So double check. This should give you 216 over 35. Okay, so these are just polynomial functions, and eventually you will get power functions that you are evaluating for these integrals. But here, a quick remark. We observe a change of integration order. Okay. So we notice that, okay, so in the previous, this is the dy dx, but now in the latter integral, it's dx dy. So we can actually interchange the order of integration. It's just the description of the bounds have to rely on the way that you specify for the integral. Okay, so and it may not be easy if you have a general region. And does it actually help when you integrate? So let's look at the next example. So let me write down the example. So suppose you're given the double integral where this is from 0 to 1 dy, and from y to 1 dx, you're integrating e to the x squared. Okay. So if you look at this double integral, so here on the inner, we are integrating with respect to x, okay? But here you're integrating e to the x squared. This is actually a function that is hard to integrate, to write down the antiderivative. Okay? So e to the x squared, we don't really have a direct antiderivative in our mind. This is actually real. We know that we are integrating. Actually, we can rewrite this kappa integral in terms of the integral over the region D of this e to the x squared function, okay, where the region is actually the following region. So we just copy from the integral definition. So basically, this is what? This is y is cut between 0 and 1, right? And then x is cut between the lower bound of y and upper bound of y. So it's actually not so difficult to establish the figure of this region. So the original integral may be hard, but once we get the description of the region, we can interchange the order of integral. So that's what we are gonna do. So here, let's see. Y is cut between 0 and 1. So 0, 1, so x, y. And then we have what? We have x is so the lower bound is y equals x, right? X equals y. So this is a line that's going from the going through the origin, right? And then we have the upper bound x equals 1. Okay, that's a vertical line. So x equals 1 right here. So I probably want to make this one a little bit higher. Right here. So now you get the point. So basically, we are describing this region that's actually what? That's actually using horizontal bars, and we know, okay, the left endpoint is y equal to x. Oh, excuse me, is x equals y. Let me reverse the order. And here, this is x equals 1. Okay, so the vertical line. So this is the region D, which is a triangle. Okay. So basically, we are looking at a very important kind of question where it's possibly hard when we start with the stuff integral in a certain order, but then we may want to interchange the order of the integration so that it becomes manageable. Okay. So here, within the integral, we see that the y goes from 0 to 1 freely, but the x is cut between y and 1. Okay, but that's actually this triangle shaded. That's called the region D. That we have the base to be y equal to 0. The right hand side boundary to be x equal to 1, and then we have the hypotenuse, which is x equal to y. Okay, so basically here, the red line segment or bar that you see horizontally, that's having the x value to be between x equals to y and x equals to 1. Okay. Then what we do is that we do this equivalence description by using vertical bars to cover this region, okay, which is equivalent to the following. So this time it's the same triangle. It's a right triangle, okay, and then we have the lower left corner 0, 0. The upper right is 1, 1. And then, okay, of course, the right hand boundary is x equals 1. And now here we're using, if we're using the vertical bars to cover this region, and then we are going to care about the y values of this line segment, right? So basically here at the bottom, of course, we have y equals 0. That's the horizontal line at the bottom. Okay, but then we want to know the y coordinate of the point at the upper bound of this line segment, right? So still on the line x equal to y, but then here we want to get the y value out of this line. So here, instead of writing x equals y, we write y equals x. Or you can say, okay, this is the equation, right? This is the function, right? But then this is the output is x, the input is y. So you want to reverse the order, or you can say we are solving the y value out of this equation, and which is trivial because we just flip the left and right hand side, right? So or y equals x. Okay, so here we see at the bottom y equals 0. On the top of this line segment y equals x, and that gives the bounds in terms of y, right? And then we see that this vertical bar can be free, starting from x equals 0 all the way up to x equals 1. Right? So these are just vertical bars covering this triangle. Right? So the equivalent description is what? It's actually saying, okay, my x is free between 0 and 1, right? And then my y value are between 0 and x. Okay. So of course, if I want to fill out every detail, I need to say this is the region D, which is all the xy pairs, such that x cut between 0 and 1, and y cut between 0 and x. Okay. Sounds good. Any questions? Okay. So once we describe it in another way, then we can describe that we can rewrite the double integral in this way in purple. Then, so basically, this double integral over the region D of, so just remember the function we integrated is e to the x squared, which is complicated. It's hard to write the antiderivative in terms of x. But now we just describe, we just rewrite this integral in terms of the purple double integral. So basically here we have x to be free, that's on the outside, from 0 to 1, dx. And then on the inside we have y between 0 and x, so starting from 0 to x. Right? And we are still integrating this function e to the x squared. Okay, so it looks really similar to the original form, but there's a clear distinction because now if you compare, so let's go up a little bit. Okay, so originally we have dx in the inner, right? It's the same function that we integrated, but now we have dy in the inner. So the difference here is that in dx, if the dx is in the inner, then we are trying to look for the antiderivative for e to the x squared, which is complicated. But now if you have dy in the inner, you're saying, okay, I have this e to the x squared, which stays a constant when I integrate with respect to y, right? So for the inner integral, the antiderivative in terms of y is trivial, right? So constant, the antiderivative for that is just that constant times y. Okay, so that's actually pretty nice. That's the difference. So this equals to, so now here we have e to the x squared, that's kept as constant when you do the antiderivative in terms of y, right? So now you multiply by y, that's the antiderivative of the function, the inner function, and then you evaluate at y equal to 0 and y equal to x. Okay, so these are the bounds. So it's good. Okay, so now we just copy the outside integral, and we evaluate Of course, when y equals x, it gives you you just substitute x in the place of y, right? But when y is 0, it gives you nothing. Okay. So now you see something really nice. So if we have e to the x squared multiplying by x, and then so we then copy the dx at the end. And now if you see this is definitely better than only e to the x squared, right? Because now we have x dx, and it looks it's giving you like a hint that okay, you should use substitution, right? Because x squared, if you use u to be x squared, then the u is 2x dx, right? So that's very nice. So u equals x squared. Use up. Because if you choose u to be x squared, then the u is 2x dx. So this is writing the differential form. And then now you want to replace x dx, right? So you can solve from this equation that x dx must be du over 2. And finally, we have x between 0 and 1. So we just we substitute everything to u, right? So when x is when x is 0, u is 1, excuse me, u is 0, u is x squared, right? When x is 1, u is 1 squared is 1. So we can do the substitution. We can translate everything in terms of u. So here it just says, okay, we have e to the u, and then x dx here becomes du over 2. And then for the integral, so the lower bound of the variable u is 0, the upper bound of the variable u is 1. Right? So that's actually now very trivial because e to the u, the entire in terms of u is itself. Right? So this is exactly e to the u, and of course the 1/2 goes in the front, and I evaluate. So now my variable is u, so it's evaluating at u equals 0 and u equals 1. So we get an answer. We get an answer that this is 1/2 e to the 1 minus 1/2 e to the 0. And we actually know that e to the 0 is just 1. Right? And we're done. So it's good. Right? So you see, in the end, we are able to get a nice answer, even though the function e to the x squared, and we'll start with this really hard to integrate. Okay, so quick remark that we can see clearly that the order of the integration could be important. Okay? Remark. Order of integration may be important. So basically, so it's an important kind of question that sometimes you may see that okay, the function that you're integrating on the inside is somehow hard to get the antiderivative. Then that's sort of a hint that you probably want to play with the order of integration to see whether the other order gives you a better calculation or not. Okay, so that's very important. All right, so now we want to talk about the properties of double integral. So that's actually a really parallel part of results or items that we want to just reuse from the previous section. So let me cheat by copy and pasting. So this is same old. So the integral, the double integral of sum of functions is going to be the sum of integrals. But here, originally we have cap R to be the rectangles, right? But here, if we are doing a general region, cap D, we just replace this cap R with cap D. Okay. Basically, for double integral of a sum of functions equals to the sum of the double integrals over the same region. Okay. And if you have a scalar modification to the in the following function, little f, then you can take that constant out. And if the third item, if you have f lower bounded by g within the entire region D, then you know that the double integral of f over the region D is going to be lower bounded by the double integral of g over the same region. Okay. And then this last item, I want to mention that we can mention the volume of the solid that's cut between f and g and above the region D. Okay, so the volume of the solid between surfaces z equals f of x y and z equals g of x y over the region D is this is going to be the left hand side minus the right hand side of the inequality from above. Okay, so the volume is just going to be the double integral over the region D of f minus g. Right. That's pretty intuitive. So basically, here, when we try to interpret this double integral, let's just say, okay, I subdivide the region D as usual, okay, into small pieces, and then for the heights of these of the sparse that we accumulate, we are using the upper bound minus the lower bound at minus g. Okay, so the maximum z value minus the minimum z value. Okay. And here we want to be sure that our functions have this relation. So f is lower bounded by g. Okay. Right. And the properties continues. So the next item. So now, if we integrate one, okay, so basically the function that we're integrating over the region D is just one, then what does it give you? So basically, you have the bottom region to be D, and here you say, okay, I'm looking for the volume of the cylindrical shape where the height is always one, right? So the value of it, of course, equals to the area of the base, right? So if you calculate this double integral, that's integrating one, then that's giving you the area of the region D. And then if cap D is, excuse me, if cap D equals to the union of two regions, where D1 and D2 do not overlap, except at the boundary. Then, of course, so we can write the double integral over the region D into the sum. Okay. But here, let me quickly draw a region D that can be split into two pieces. Okay, so basically, we just want to make sure that the two regions only overlap at the boundary. Okay, so as a illustration, this is region D1, this is region D2. Okay, so you can see here that D1 and D2 they only intersect at this boundary right here. Right? Okay, if this is the case, then the interior of these regions will not overlap. Okay? Then we can split this integral over cap D into two pieces. Okay? So then the conclusion here is that the double integral over the region D of some function f of x, y, dA is equals to the sum of the double integral over the region D1 plus the double integral over the region D2 of the same function. All right. Okay, now let's look at another example. So here, this is something we have seen from Calc II. Okay, so this kind of function, basically finding the area, find the area of region cap D bounded by several curves. Okay, bounded by, here we have y equals x squared, y equals negative x plus 12. And finally, we have y equals to 4x plus 12. All right, so here we have a parabola and we have two lines, right? So of course we want to sketch the region first. Let me make it a little bit more vertical. Okay, so now firstly, of course, the parabola. Okay, so this is y equals x squared, x 0 y. Okay, we have a line, we have negative x plus 12, and we have 4x plus 12. So you see that there's a common y-intercept, right? So the y-intercept is 12. So basically we have, let's say this is 12, and then so we have a line that's decreasing, and we have a line that's increasing with a larger slope. Okay. But you probably get the idea because we have the region that's enclosed by these curves, right? So here the region D is actually so it's bounded by the parabola and also the two lines. So we can expect that that's the region here. Okay. That's the region enclosed by the parabola and the lines. Okay. So now here, of course, just following the logic that we have been doing for these regions, we definitely care about the intersections. Okay. So of course, firstly, the intersections. So here we have the parabola and we have two lines. Okay, so there's two systems of equations that we need to solve. The intersection can be solved by the following. So basically here we have the parabola y equals x squared, we set it equal, we set it to be simultaneously satisfied with, let's say, 4x plus 12. Okay, so this gives you, and here, so, okay, so the line here, this is y equals 4x plus 12. This is the increasing line, y equals to negative x plus 12, that's the decreasing line. Okay. And here, for the increasing line, actually, if you imagine, so the line will intersect this this parabola on the right hand side at some point far away. Okay, so here it's although it doesn't seem to intersect within the picture, right? But then we are looking for the smaller solution, right? Because we have the intersection right here. So that's the solution that you want to identify. Okay, so although there must be two solutions, but we select the smaller one. And you can definitely do that yourself. It shouldn't be too hard. So this should give you x equals -2 and y equals 4. And similarly, for the other line, so the line like this, we can extract this intersection right here. Okay. So, but we are looking for the larger one. So also solve for the second system. You should get x equals to 3 and y equals 9. So now we can get the intersections 3, 9 and -2, 4. Okay. So okay, so now we get the x and y coordinates of the intersections, right? So here comes my question. So any questions so far? You get the intersections. Okay, so now here comes my question. So here we know, okay, we have the smallest x value of this region to be -2 at the left endpoint, the left intersection. The right intersection is 3, 3, 9, right? So it's tempting to write the interval as dx on the outside where I have -2 to 3. And here, I can use my x squared as lower bound for y, okay? Because here this parabola is lower, right? But then, what do you think if I put the upper bound to be this line, and then I integrate 1? So does this double integral represent the region that I want? So I see some of you say no. What's the reason?
Until x 0.
So yeah, okay. So I see I hear an answer that it only applies to up to x equals 0 right here. And it cannot go beyond because on the other side we have this upper bound, okay, instead of the purple line on the left. Exactly. So basically, if you this is not exactly the correct answer. Because exactly, so for y, if you use that purple line in the answer, it will be an overshoot. Okay, so that will give you this part, and you end with the x value here, which is too much. Okay, that's too much. So this is the wrong answer. This is the region that's enclosed by the lines. Okay. So here we see that we cannot really use a single integral to represent this area. Okay. So which is why we want to split it into two pieces, where we have the piece on the left ending at x equals 0 to be d1, and here the other piece is d2, where it starts with x value 0 and ends at x value 3. Okay. Okay. And so I would say essentially this is probably something you have seen already from Calc 2, but here we just want to emphasize this that it is in a certain way you probably have to write this integral into two pieces. Okay. Well, and here, okay, let me quickly mention that we do have another intersection in solid black, which is 0, 12, right? So 0, 12 is the common y intercept. Okay. So y intercept of the lines. So here we just say the total area of the region D is the sum of two pieces is the integral over d1 integrating 1 plus the integral over d2 integrating 1. Okay. And here we see that so d1 goes from -2 to 0. Dx. So d2 goes from 0 to 3. Dx. And then for y, here we have x squared in the lower bound, and that the increasing line is x plus 12, I believe. And then for the other piece, I have the lower bound to be the same parabola. The upper bound is negative x plus 12. Okay. And here, I just want to quickly mention that even if you don't write this y, it's still fine. Okay. So when you're integrating 1, you can omit that 1 in your integral. If we are integrating one here, we may skip right here. Okay. So of course now when you integrate the things, you will see okay, this integral with respect to y, the value is just gonna be just gonna be the upper bound of the integral minus the lower bound, right? So that's the polynomial in terms of x, and it's the same for this one. Okay, so upper bound minus lower bound. So this is exactly why this kind of question is directly related to what you have learned in Calc 2. But of course, in general, you will be integrating some function little f. Okay, so then that will be a little bit different. So in that case, you will have little f very well, and then that will be the distinction between Calc 3 and Calc 2. Okay, so finally, I just want to quickly mention the answer of this integral. And so make sure to double check. It should be 215 over 6. Okay, so any questions before we move on to the next section?